Welcome to the lesson on section 7.4, Derivatives of Log Functions. In this lesson, you'll learn about derivative formulas for the natural log of x and log base a of x, and you'll learn about a process called logarithmic differentiation. Consider the equation y is equal to the log base a of x. We're going to derive the formula for the derivative. First, write the equation in exponential form. This would mean the same thing as a to the y power equals x. Using implicit differentiation, we get a to the y times the natural log of a times y prime equals 1. Isolating y results in 1 over a to the y ln a. And then using a to the y is equal to x from our first line to substitute, we get 1 over x ln a. So the derivative of log base a of x is 1 over x ln a. What if we had a base of e in place of the a? Log base e is natural log, and the natural log of e is 1. So we find that the derivative of the natural log of x is 1 over x. If we have anything more complicated than x in the natural log, we have to use the chain rule. For example, the derivative of the natural log of 3x squared would be 1 over 3x squared times 6x, or 6x over 3x squared. Here's a summary of all the log-related derivatives we've found so far. Each row is really the same rule, just written with or without the chain rule. Of those three formulas, you should only bother to memorize the one for the natural log of x. If you needed to find the derivative of log base a of x, you could use the change of base formula to rewrite it as ln x divided by ln a. And the derivative of that, since ln a is constant, is 1 over ln a times 1 over x. To derive the formula for the derivative of y equals a to the x, we'll first need to discuss a technique called logarithmic differentiation. Logarithmic differentiation is most useful when we need to find the derivative of an expression consisting of a variable base raised to a variable exponent, or when we need to take the derivative of an expression containing many exponents, multiplications, and divisions. Consider the function f of x equals x plus 1 to the x power. To find the derivative of f, it would not be appropriate to use the power rule, because the power rule is used for variable bases raised to constant powers. We wouldn't use the exponential rule, because the rule is reserved for a constant base raised to a variable power. We'll use logarithmic differentiation here because we have variables in both the base and the exponent. First, take the log of both sides. Then, use one of the laws of logs to bring the x out of the exponent position. Take the derivative on both sides. Here I had to use the product rule on the right side. Isolate y prime by multiplying both sides by y. And then we substitute the original expression in place of the y. A case in which logarithmic differentiation can make something you already know how to do easier is when we have an expression full of products, quotients, and exponents. Here we have y equals x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th power. Take the natural log of both sides first. The properties of logs allow us to rewrite the products, quotients, and exponents in this way. Take the derivative of both sides, and then isolate y by multiplying both sides by y, and again substituting the original expression in place of y. In this example, we're going to use a graph or a table to estimate the value of each of these limits, and then we'll make some conjectures about the exact values. So let's start with the first limit. I'll enter y equals 1 plus 1 over x to the x power in the y equals screen on my calculator, and set my table to start at a large value of x and go up by a large increment, such as 10,000. I can see from my table that the y's appear to approach 2.7183. Moving on to the next limit, 1 plus 2 to the nth power appears to be approaching 7.389 as n goes to infinity. And the last limit goes to approximately 20.085. Can you guess what the exact value of these limits are? They are e squared, and e to the third. Based on what we just found, what can you conclude about the limit of 1 plus r over n to the nth power as n goes to infinity? If this pattern holds, this limit must go to e to the r. One significance of this finding is related to compound interest. Recall the formula for calculating an account balance after t years compounded over n periods per year. Continuous compounding could be represented by an infinite number of compounding periods per year. The limit of the red part as n goes to infinity we just found is e to the r. So the limit of the account balances as n goes to infinity would be p times e to the rt, which is the formula you learned in Algebra 2 for continuous compounding. We'll actually prove this using limits at the end of this unit. This concludes the lesson on section 7.4, Derivatives of Log Functions.